Lesson 4, Day 2, Writing Numbers in Scientific Notation. 7 nanoseconds is equivalent to 7 1/billionths of a second, or 0.000000007 second. Write 7 1/billionths in scientific notation. So just like in day 1, you needed a number that's greater than or equal to 1, but it's less than 10, and you need to multiply by a power of 10. So the first thing, we know that our whole number, or our number, should be 7, because that's the only number we were given that's not 0. And we're going to be multiplying that by a power of 10. Now, to get from 7 to 7 1/billionths of a second, 7 is way bigger than 7 1/billionths. So what you have to do to get back from 7 to 7 billionths, you need to move your decimal place to the left. So we'll be moving it, since we're moving to the left, then our exponent needs to be negative to show that we're moving to the left. So if we have 1, 2, 3, we have 8 of them, I think. 1, 2, 3, 4, 5, 6, 7, 8 of those. If we need to go from 7 to here, then we've moved our decimal place 1, 2, 3, 4, 5, 6, 7, 8, 9 times. And just to make sure we're correct, we go back from 7 and move 1, 2, 3, 4, 5, 6, 7, 8, 9. Add in your placeholder zeros, and we should have 8 zeros in front of our 7. So we moved our decimal place a total of 9 times, which is correct. And so now let's break it down a little bit further. So we have our answer here, which is 7 times 10 to the negative 9. The negative indicates that we've moved to the left. And then, of course, the 9 tells us we move to the left 9 times. All right, so in the picture it, and I'll go ahead and erase this because we don't really need this anymore. Look at the patterns in the chart below. 100 is equal to 10 times 10, and that's 10 squared. 10 is 10 to the first. 1 is 10 to the 0. 0.1, which is 1/10, is equal to 10 to the negative 1, and then so on and so forth. The modulo says you can write the decimal as a fraction, and you definitely could do this. So they first wrote it as 7 over 1 billion, and then they just multiplied, they broke it down even further. They pulled out the 7, and they multiplied it by 1 over a billion. And they then saw that 1 over a billion is equal to 1 over 10 to the 9th, and we can use our negative exponent rule. So write that on your paper as well. And they know if they have 1 over 10 to the 9th power, they can rewrite that as a negative exponent. So they can just give me the reciprocal and the opposite exponent. And of course, we know anything over 1 is just itself. So that's 10 to the negative 9th. Let me write that over here. Is our power of 10. So then you can write, so that's one way you could do it, is you start off by writing the decimal as a fraction. We knew that the 7 was in the billions place, so it's just 7 over 1 billion. And then change your 1 over 1 billion to a fraction with the power of 10, and then go back to your negative exponent rules and change it to a negative exponent. The next way you could do it is you can write the number as a product of a number that's greater than or equal to 1 but less than 10 and a power of 10. So then now that you know that you have 7 times 10 to the negative 9th, you just put them together. 7 times 10 to the negative 9. So move the decimal point 9 places to the right to get a number between 1 and 10. And that's what we did. That's what I actually did in the beginning. Because I already knew how to do it. So that's different because I knew how to do it. If you didn't know to do that, then you can go through these steps like in the model it. So to solve it, we had Our original number, we moved the decimal place over 9 times to get a number between 1 and 10. Our number ended up being 7, and we moved our decimal 9 times. All right, so because the number is less than 1, the exponent is negative. The absolute value of the exponent is equal to the number of places the decimal point moves to get the number between 1 and 0. That's very important. Please put a cloud or something around this statement so you understand what our exponent actually represents. It represents the number of times we've moved, and if it's positive or negative, it just tells you which direction you moved. I like to think of it that way. All right, and let's go ahead and move on to the connected. All right, connected. Now look at different ways to solve the problem. So number 2 says write 1 billion as a product of tens. So we have 10 times 10, that's 100, 1,000, 10,000, 100,000, million, 10 million, 100 million, billion. Okay, so I just constantly keep going by tens until I get to the number I want. So then it says write 1 billion as a product of 10 or a power of 10. So we've got 10 multiplied by itself, so that's our base. And it's multiplied by itself 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So 10 to the 9th power. Look at the table on the previous page. Write 1 over 1 billion as 10 to a power to complete the equation. We've got 7 times 1 over 10 to the something, so it's going to be 10 to the negative 9th. We already had our power up there because we already wrote a billion as a power of 10. So it'd just be 7 times 1 over 10 to the negative 9th, which is equivalent to that. Number 5, look at solve it. When you have to move the decimal point to the right to express a number in scientific notation, will the power of 10 be positive or negative? So when you move the decimal point to the right, just like we did here, we had 0 point, all those zeros, I think that's it. And we moved it to the right to get a positive 7. Then since we had to go from this number, this really small number, when we went from a really small number to a larger number, then our exponent actually needed to be negative because we made the small number large. Okay, so it needs to be negative when you do that. So when a number is in, it'd be the opposite way. So if we went from a large number to a smaller number, so if I had like 7.1 million, then I'd say that's 7.1 times 10 to the, because I'd have to move my decimal point to the left to make it 7.1, and I'd say 1, 2, 3, 4, 5, 6. So I move it left 6 places. Okay, but I moved it left, but that doesn't really mean it's actually negative. I need this to be a positive exponent because 7.1 is much smaller. I need to make that number bigger in order to get it back to 7.1 million. Okay, so it's actually thinking about it in the opposite way. Number 6, when a number is written in scientific notation, a blank exponent means the number is at least 1, and a blank exponent means the number is between 0 and 1. So a negative exponent is going to mean that that number is very small. And a positive exponent means that the number is at least 1. Okay, like this one, really big. We've got 7.1 times 10 to the positive 6. That was 7,100,000. But when we had a negative exponent, 7 times 10 to the negative 9th, this number was so small. It was way smaller than 1. Okay, well, it was way smaller than 1, so it's between 0 and 1. So when we have a negative exponent, it's pretty much a decimal number. And when you have a positive exponent, it's a big number for the most part. All right, number 7 is 2.14 times 10 to the negative 5th, at least 1, or between 0 and 1. It's going to be between 0 and 1 because the exponent's negative. Of course, we just learned that. So you'd be moving the decimal 5 places to the left. And we can do that just to make sure that we understand what's happening. So that's actually what's happening in number 8. Write 2.14 times 10 to the negative 5th in standard form. So the first thing they did is they wrote both factors as fractions first. So they had 214 over 100 because the 4 is in the hundreds place, so they just rewrote it that way, times 1 over 10 to the 5th power, so they use their negative exponent rule here. That's great. Love bringing that back in. All right, so then when you do that, you just multiply straight across. We have 214 over 100 times 10 to the 5th power, which is 1, 2, 3, 4. Yep. Yeah, 5 of those zeros. Okay, and then we'll have 214 over 1, 2, 3, 4, 5, and then 2 more zeros. It's a really small number. Okay, so then if I want to write it in standard form, that's actually going to be equivalent to, I have my 214, and I'm going to move that over 1, 2, 3, 4, 5, 6, 7 times. 1, 2, 3, 4, 5, 6, 7 times. 1, 2, 3, 4. So in standard form, I have 0.0000214, which again, you could have just done that by starting with your 2.14 and moving your decimal place 5 places to the left, because our negative 5 tells us that we're going to move to the left 5 places. If it was positive 5, we move to the right 5 places. But since it's negative, so the negative exponent, again, it means to move to the left. All right, so you move it 5 places to the left. 1, 2, 3, 4, 5. And you got your decimal point, fill in your zeros. And we've got the exact same thing we had here. I like moving on to this step instead of going here because it can be a little bit confusing with all of the huge numbers you have to deal with. But if you wanted to know where it comes from, then yes, this is telling you why number 9 works. All right, and then moving on to the try it. Please take a moment, if you haven't already done so, to actually try it on your own and then check yourself with this. All right, let's go ahead and review our try it. Use what you just learned to solve these problems. Show your work on a separate piece of paper. So we want to write, number 10 says first, write 63,120,000 in scientific notation. So it needs to be a product of 2 factors. The first factor needs to be between, I think it said between 1 and 9. So something that's smaller than 10. So let's go ahead and write that as 6.312. All of our factors, or all of our digits that aren't 0. And then, of course, we needed to make sure it was smaller than 10. So we had to choose to have it there. It needed to be between 1 and 9. So that times our power of 10. So we would actually have to move our decimal point to get back here. To get here to 1, 2, 3, 4, 5, 6, 7 times. And of course, since we actually need this number, we went from a large number to a small number, then our exponent needs to be positive. And I'm saying large because that's our original number. But then if we need to go from a small number, a smaller original, to a larger number, like if we're going from something that's like 0.009 to 9 times 10 to the negative third or something, then our exponent would be negative, because we're going from a small original to a large factor. All right. And then number 11 says write 9.054 times 10 to the negative 6th in standard form. So we'll start with our factor, and it says we're moving it, since we're multiplying by 10 to the negative 6th, we're going to pay attention to our exponent, and we're going to use that to let it tell us which direction we need to go and how far we need to move. So the negative tells us to move to the left, move our decimal point to the left 6 times. 1, 2, 3, 4, 5, 6. Place your decimal. 1, 2, 3, 4, 5, and then fill in your zeros. So in standard form, we've got 0.5 zeros, 1, 2, 3, 4, 5, and then 9054 is our solution. And that is it for day 2.